Okay, hi guys, good afternoon. So, um, so today good afternoon. Today I just wanted to talk to you guys about the symmetric group. Okay, so I just want to talk to you guys about the symmetric group and a few like technical stuff. Okay, so let's just remind ourselves of like what is a permutation? On the symbols 1, 2, 3, 4, all the way up to n. Well, permutation is just a bijection from this set to this same set. Okay, and then if we gather up all the permutations, so the set of all permutations is denoted Sn. And Sn becomes a group where the group law is composition. I guess we can call it the group law. Sigma tau. Oh, can I zoom in? Yes. I can try. Is that better, or maybe hopefully not worse?
Thank you, sir.
Okay. Okay, so we have all these permutations, and if we have two of them, to combine them, we just make a new map. You know, so how should we denote this? Well, I is just going to get mapped to sigma of tau of I. Okay. I guess we could put like this colon to mean like define. Okay. So once we have that, we can do all our regular calculations. I put I think an example of a calculation in SN on the assignment 2. Okay. But we need to talk about like a special kind of, like, we have a notation for a special kind of permutation, and that is a cycle. Okay. So let A1, A2, up to AR be distinct. Then use this notation, write down all the symbols in brackets, and then this is the permutation. That sends that maps A1 to A2, A2 to A3. It maps AR minus 1 to AR, and then it maps AR to A1, and it leaves everything else alone. And it leaves everything else fixed. Okay. And this this A1, A2 up to AR, this is called an R cycle. An R cycle. Okay. Okay, so like for example, let's work in S4. We have the 4 cycle, 1, 3, 2, 4. And then this is the permutation, which sends 1 to 3, 3 to 2, 2 to 4, and 4 to 1. Okay. So using the notation that we write the elements of the domain above and what they map to below, we could write, so like we write 1 gets sent to 3, 3 gets sent to 2, 3 goes to 2. 2 gets sent to 4, 2 goes to 4. 4 goes to 1, so we put a 1 there. Okay. And you can see this permutation kind of goes in around and around in a loop. 1, 3, 2, 4, 1, 3, 2, 4, on and on. Okay. And then okay, as another example, in S5, we have this 2 cycle, 1, 3. This is just the permutation which sends 1 to 3 and 3 to 1. And then everything that doesn't appear stays the same. Okay. Okay. And so it would be nice, there is a way to switch between notations, and there is. Proposition. Just a moment. Okay, sorry about that. Right. And I'll write down the proposition, but it's really more important to just be able to do this kind of this method. But let me write down the proposition. So let sigma be an Sn, and sigma can be written as a product of disjoint cycles. Okay. Okay, and we're not going to prove this, but it's kind of better to just learn how to do it. So, and I'll try to explain it in two different ways. Okay, so let's figure out how do we write a permutation as a product of disjoint cycles. Well, I guess I should say it can be written uniquely up to reordering of the cycles. Okay. Okay, so let's just try and let's just write down a permutation and then see if we can write it as a product of disjoint cycles. Okay. Okay. And now I'm just going to write down I'm going to rearrange these in some order. I don't know. 3. So I have to make sure not to write anything, to repeat anything, I guess. So let's have 5. Let's see, I still need 8. And 9 and 2. Okay. Okay, so now let's try and unravel things in terms of disjoint cycles, right? And so the strategy is to start with whichever symbol and follow it. Okay, so let's start with 1. And then 1 gets sent to 3, so we write 3 next. And where does 3 get sent to? 1. Okay, so that's one cycle. Okay, that's one of the cycles of sigma. Okay, and then so we've kind of checked off the symbols 1 and 3. Now we look for a symbol which we haven't encountered yet. Let's start with 2. And we follow that. So we follow from 2 to 4. Where does 4 go? To 5. 4 goes to 5. What about 5? 5 goes to 10. And 10 goes back to 2, so we close it. Right? So now all the information about what happens to 2, 4, 5, and 10 is included in this cycle. This cycle says 2 gets sent to 4, 4 goes to 5, 5 goes to 10, and 10 back to 2. Okay, and then there's still some information left. We have to figure out what happens to 6. Okay, so if we start with 6, 6 goes to 11, 11 to 9, 9 goes to 8, and 8 goes back to 6. That's the end of that cycle. And then The only thing we haven't seen is 7, and 7 is gets sent to 7, so we just leave that off. Okay. Yeah, so if we want to, that's fine. We would just put it by itself. But often we don't include it. But if you want to, I understand. Okay. That brings me to another point. You know, we have the identity permutation. We would just write the identity permutation as a one cycle, as this one cycle, meaning this is a permutation that sends 1 to 1 and sends everything, like fixes all the elements of 1 up to n. Okay. Okay, so now this encodes completely all the information you'd want to know about, all the information about what sigma does to the different things from 1 up to 11. You know, you want to know what is sigma of 5. Well, you look for 5 in one of these cycles. Here it is. And then the next one is 10, so that just means sigma of 5 equals 10. Also notice that by doing this process of following what happens to sigma, like if a number is included in one of these cycles, it's not included in any of the other cycles. So very naturally, all the cycles are disjoint. Okay. Okay. So you can write and so the reason why we might have this disjoint cycle notation is because it's a little bit easier to do to work with in this form. Okay, it's like more compact, and it's easy to do things like calculate sigma squared. Okay, to do that, so let's try and work out what is sigma squared. We just need to write down a few facts about cycles. Right. Okay.
So when you say cycle decomposition, is that considered the same thing you do just now?
Yeah. Oh, I'll just put a label. This is the cycle decomposition. Or I guess I should say disjoint cycle decomposition. Okay. Right. Well, sometimes I like to draw a picture with this, so I'll try to draw a picture. Okay. All right. Okay. So our sigma sends 1 to 3 and 3 back to 1. Okay. So if we just draw all the numbers, all the symbols from 1 up to 11 as little like dots, and then draw an arrow to mean from one dot to the other to mean like sigma maps. So this arrow means sigma of 1 equals 3, and this arrow means sigma of 3 equals 1. Then we can like visually see what's happening. Right. Oops. Okay. Here's a picture of all the different cycles of what happens to every symbol once you apply sigma. Okay, and they are just they just live in their own spaces, you know, separate from each other. Okay, so now if I want to do something like, and you notice like the different cycles, they don't interact with each other. That allows us to write down the following convenient fact. Well, I guess I will just call it a proposition as well. Disjoint cycles commute. Okay, and let me explain what that means. Okay, by an example. Okay, just a moment. Excuse the interruption. Okay, sorry about that. Right, so let me just explain by example. You know, here's a couple disjoint cycles, 2, 3, 5, and 1, 4. Both elements. Let's call this sigma. Let's call this tau. Both elements of S5. Okay. Then we can compute. So like sigma, if we write it out, it's this permutation. 2 goes to 3, 3 goes to 5, and 5 goes to 2, and 4 and 1 are left alone. And then tau is like this. Okay. Now we can compute sigma tau. And we can also compute tau sigma. And how do we compute sigma of tau? Well, you start with 1. We compute tau of 1, and then sigma of that, whatever tau of 1 is. So tau of 1 is 4, and then we do sigma of 4. So tau of 1 is 4, and then sigma of 4 is 4, right? So because 1 and 4 only appear are only changed by tau and not sigma, the sigma does nothing, right? It's just, and then we look at sigma tau of 2. Well, tau appears in sigma, but it kind of doesn't appear in tau, so the tau doesn't do anything here. So tau of 2 is 2, and then we do sigma of that. Sigma of 2 is 3. Again, 3 appears in sigma, not tau, so we can kind of ignore tau. So sigma tau, so tau of 3 is 3, and then 3 gets into 5. And what about 4? 4 gets into 1 by tau, and 1 gets fixed by sigma. And then what about 5? 5 gets fixed by tau, and then 5 gets into 2. Right. And notice there's like, whenever we were computing things, the symbol was only changed by at most one out of the 2 permutations. And the same thing is going to happen when we do tau sigma, right? if something is changed by sigma, it's not affected by tau. So what happens? Well, when you do sigma first, you go gets sent to 1, and then 1 gets sent to 4. You get 1, 4. We get the same thing happening. So, for example, sigma of 3 is 5, and then tau of 5 is 5. So tau sigma of 3 equals 5. And then the same thing happens. Right? So disjoint cycles commute, because when a symbol appears in one, it doesn't appear in the other. Okay. Okay, so in this case, we write sigma tau equals like that. Right? And that's the same as, okay. And another thing that might be useful to working with cycles is that a cycle doesn't matter which one you start with, right? So a cycle is really like a loop or something. Like in this cycle, you can start with any one of the 4, right? The way I wrote it down was 2, 4, 5, 10, but that's the exact same cycle as the one that would go 4, 5, 10, 2. Okay, so let me write that down. Okay, so just notice by example 2, 4, 5, 10. That's the same cycle as 4, 5, 10, 2, which is the same cycle as 5, 10, 2, 4. The same cycle as 10, 2, 4, 5. Those are all the same. Okay. It is also having things in cycle form allows us to also compute powers of a permutation more easily. Right, let's go back to our example sigma. I'll just peek and write it, copy it down again. Here's sigma. Well, we can try and figure out what is sigma squared. Well, sigma squared, if we write it out, we can write it out like this. And then, so that's 1 sigma, and then we write down another sigma. Then I have to go down to the next line. Okay. So all I did was write sigma next to itself. That's sigma squared. But remember, all these cycles are disjoint, well, except for these two, right? So that means like this cycle, we can switch it so it lives right next to its twin, right? Because 1, 3, the cycle 1, 3, and the cycle 6, 11, 9, 8 are disjoint. So they commute, that means we can switch them. Okay, so let's do that. Well, what happens is we have 1, 3 times 1, 3. We have 2, 4, 5, 10. And we can move this next to this one. And then we have the same thing for the last cycle. Okay. And now let's figure out what happens when we square each of these cycles. Well, when we do 1, 3, and then 1, 3, 1, 3, switches 1, 3, and then this other one switches them back. Right, so after doing this, essentially we've just left one, like we've left 1 and 3 alone. Okay. So just as an aside, 1, 3 squared is just the identity. Right? Because this one says, all it says is switch 1 and 3. And if I switch 1 and 3 twice, I haven't done anything at all. Okay. And what about 2, 4, 5, 10 squared? Well, the first one says send 2 to 4. The second one says send 4 to 5. So when I apply this 4 cycle twice, it kind of has the effect of like skipping one of the things. Okay, so I get a 2, 5, and then when I skip again, I go from 5 back to 2. And what about if I start at 4? Well, if I start at 4 and skip, I go from 4 to 10 and then back to 4. Okay, and then if I do 6, this 4 cycle twice, well, when I do it twice, it has the effect of like skipping 1, right? So I get 6, 9, and I get 11, 8. So this is sigma squared. Okay. And if I go back to the loop, well, I won't go back to the loop. Okay, for now. Okay, so now is actually a good time. We should take a break. Oh, just a moment. Okay, sorry about that. So there's a question. Can you show an example? Yes. Let us just take a quick, like 2-minute break where I have to restart Zoom. So let me just take a quick break. When we come back, we'll do more examples of cycles. Okay. So I'm gonna end the meeting now. So just use the same link again.